We left off with our plate tectonic story with finding that the ocean floor isn't flat like everyone expected. It actually has a really long mountain chain winding all through the oceans. These are called mid-ocean ridges. Okay? Here's mid-Atlantic is a typical one. We also found that it was hot in the middle of this, in the valley of this mid-ocean ridge. And we need to figure out why it is. Before we do that, though, we have to take a quick break and relearn the layers of the Earth. Hopefully you've learned these before, so we're just going to go through them really quickly, because it's important that we know what the inside of the Earth looks like so we can explain the next mechanism that we're going to get. Okay, you probably know, hopefully know, the center of the Earth is the core. Okay, core is made of two parts. There's a solid inner core surrounded by a liquid outer core. Okay, so solid inner core surrounded by a liquid outer core, mainly made of iron and nickel. Surrounding the core is the mantle. Okay. The mantle is split into three layers. We're going to kind of ignore the bottom one. It doesn't really affect us here. But so on your picture, we have the two layers of the mantle. We have the plastic part of the mantle and the solid part of the mantle. Plastic just is a slowly flowing liquid, like really slowly flowing. And so, okay, don't think of it like water. Think of it like really, really, really thick peanut butter, like that, really slowly flowing. Okay? So that's the mantle. And then the outer layer that we're on, that's the crust. And again, I split that into two parts. I split that into ocean crust and continental crust. Ocean crust is really thin. That's going to be important for our part of the story, and it's dense, made of basalt. Continental crust is thick and not dense, made of more granitic rock. Okay. The boundary between the crust and mantle is called the Mohorovic discontinuity, or MOHO for short, because it's hard to say Mohorovic discontinuity. Okay? And I'll tell you a story about Project MOHO. It's kind of a funny story about an attempt to drill down to the MOHO. The MOHO was found by a Serbian mathematician, Andrija Mohorovic, long time ago, and using earthquake waves. And we're going to talk more about earthquake waves in just a second here. Okay, so those are the basic parts of our Earth. Now, when we're talking, the core doesn't really factor into this yet. The core is going to be important for the rest of our story, but it's this crust mantle idea that we really need to learn about first. This plastic part of the mantle we're calling the Asthenosphere, and you see it written here. So the Asthenosphere is the plastic part of the mantle, okay, the slowly flowing part. The lithosphere is the hard outer part. Okay? The lithosphere is basically fused onto the crust. Okay, we have the continental crust here, the ocean crust here. So it's not like the ocean water is sitting on the mantle. Okay, underneath the ocean water is the ocean crust, the oceanic crust. Okay, so we have core, mantle, crust. Now we know asthenosphere and lithosphere. Well, have we dug down into these layers? No, not even close. We haven't even made it out of the crust. So how do we know about all these layers? First way that we started learning about them was with earthquake waves. Okay, whenever an earthquake happens, it gives off lots of different types of waves, and we're going to talk about them in the earthquake unit. But two of the waves that it gives off are body waves. Okay? One of the body waves is called P waves, primary waves, they're compressional. S waves are secondary waves, they're transverse. Okay? But anyways, these P waves and S waves go through the Earth from the earthquake. So wherever the earthquake is, they cruise through the Earth. You can see that they don't just go straight. That's because there's density differences as you go through the Earth. So these P and S waves bend because of density. Okay. Also, something that you need to know about S waves is that they don't travel through liquids. Okay. S waves don't travel through liquids. P waves, they can go through anything. S waves can't go through liquids. So if an earthquake is produced, and these P waves and S waves are going through, and they go through the crust, they go through the mantle, they get to the liquid outer core, and the S waves stop. Okay? Because of how they travel. We'll talk about that in the earthquake unit. The P waves, though, being compressional, the P waves can go right through that liquid outer core. Okay? So it creates a shadow zone. Okay? If there's an earthquake here, you can't feel the earthquake or detect the earthquake in this big shadow zone. Also, because of the density difference, you see these P waves, they straighten out because it's really dense, iron nickel. Because they straighten out, there is another shadow zone here too. So a shadow zone here, and a shadow zone here. Okay? By how big those shadow zones are, we knew how big the liquid outer core was. Okay? So we knew that there was a liquid outer core because the S waves didn't make it through. So we knew there was liquid in the Earth. We knew how big that liquid part was because of how big this shadow zone was. We knew that there was a solid inner core because of how big this P and S wave shadow zone was, this area where you can't find any. You see this picture. Now they say the earthquake's up here, and the waves are going through. We have our shadow zone here, no waves detected here and here. Okay? So again, we're able to figure out that we have a liquid outer core, a solid inner core. We know exactly how thick everything is. Let's look at this animation here. If it'll let me look at this animation. Okay, let's try this again. There. So this animation shows these waves going through. So here's the Earth, and we're going to start the earthquake. So earthquake. P waves are the fast ones, that cyan color. The red ones are a little bit slower, the S waves. You see the red ones, the S waves are getting absorbed by the outer core, right? So we know it's liquid. These P waves are much faster. They stretch out and make it through. And they made it through in, what, 20 minutes. They make it all the way through the Earth. S waves are still going because they're slower. But again, we see this shadow zone here. So we know what the layers of the Earth, how big they are. We can also figure out their composition by the speed. Okay? So that's how we know what they are. So we start the earthquake again. You see these waves going out. P waves go right through the liquid. S waves don't. They straighten out. We get this shadow zone. So we know how big the outer core is. We know what the composition is with the speed as it goes through. Okay. So they did that. They used earthquake waves trying to figure out all the parts of the Earth. There are some places, though, that you don't have earthquakes in. Like you think of Texas. There aren't really any earthquakes in Texas. So how do they know what it looks like beneath Texas? They kind of made their own earthquakes. They set off bombs. And those waves, again, would go through the Earth. They started at a certain time. They'd have people stationed around the world with stopwatches, waiting to record these P and S waves. They even had some shaker trucks in places where they couldn't set off bombs that would just shake the Earth and send waves going through. Okay? So they were able to figure out what the Earth looks like mainly using earthquake waves. Now that's going to be important because we said it was hot in those valleys. Okay, remember, it was hot in these valleys. Well, why might it be hot? Well, do you remember what this asthenosphere was like? Okay, that's a little hint for the next one. So the next lesson, we're going to really confirm Wegener, and we're going to hopefully come up with a better mechanism for moving the continent.